Mm-hmm. You're on it. Mm.
Uh, Did even plug this guy in? At least it should be plugged in. All right, hello everyone. Can you guys hear me all right?
Yes.
Okay, great. Okay, we can go ahead and get started. So this is the memory safety review session for 161. So we're going to be going over some memory safety vulnerabilities and then how to defend against them. And then we're going to have two exam questions for you guys today. So just to start off with the basics here. So in our memory, we have our stack that's growing down from the top of our memory block. And then we have our heap that's growing upwards. So the stack is where we keep all of our function frames. So as we execute different functions, those functions call another function. All of that data is sort of being held in the stack. The heap is the memory that's used to that we have to allocate. So we can dynamically allocate memory and that will be stored on the heap. And the static section is where we store constant strings, buffers, anything that doesn't sort of change throughout the execution of our program. And lastly, the code section, which is at the very bottom, which stores all of our actual source code. So I guess one more thing is that as we execute the program, we're going to be keeping track of three different sort of key pieces of information that we store in registers. So this is the EIP, ESP, and EBP. So this is a sort of normal stack frame. So you can think about a C function. You can see the source code for orbit here. And as we execute some function, for example, orbit, we're going to have some stack frame that's keeping track of the variables of that current running function. So in this case, we define a buffer called buff. And so that bit of information has to be stored on the stack somewhere. And along with that is the EIP, ESP, and EBP, which is stored for each stack frame. So each stack frame has its own EIP, which is where in the code section that function is executing from. And the ESP is sort of where on the stack we are adding new variables to. And the base pointer is where did the start of our function frame begin. So we do want to know how to draw a stack diagram. So this helps with our sort of analyzing functions for memory safety vulnerabilities. So here we can see that we have an RIP. Can you guys see the slides properly? Should I reshare? Okay, is this better? Oops. Yes. Okay, great. Okay, so this back here. Okay, so the first thing that goes on our stack frame is the RIP and the SFP. So the RIP is the saved instruction pointer. So we have some instruction pointer that's pointing to where the code is executing, that's EIP. And then once we want to move to a different function, we store the previous function's instruction pointer in our RIP. The SFP is the saved base pointer. So as we move from one function to another, we need to make sure to store where the previous function's base pointer is. And then as we define more variables, for example, above here, we can see that we're storing it in little endian. So the least significant byte is stored at the smallest memory address. So to go over an example of how we can call a function. So calling convention just tells us what are the steps that we take when we go from one function call to another. So when main calls orbit, what are the steps that we need to do to alter the stack frame? What is the exact process that looks like? That's calling convention here. So the first thing we do is we push the arguments onto the stack in reverse order. So in this case, orbit has two arguments, two integers, arg1 and arg2. These are both arguments that we're passing into orbit. This is what's pushed onto the stack first. So we can see here, we have the RIP and SFP main. And the first thing we're going to do is push arg2 and then arg1 onto the stack. So as you can see, the EBP is pointing to the sort of base of the main function, which is usually the SFP of main. And our stack pointer is going to go down as we add the two arguments onto the stack to keep track of where our current where on the stack we currently are. So then we add in the RIP of orbit. So this is still something that the main function does. It needs to sort of save its current instruction pointer, so whatever is executing main, and then it has to move the EIP to whatever the address of orbit is. Okay, so after it changes the EIP, now we're officially executing orbit, the function orbit. So we can see here, the EIP goes from the code section of main to the code section of orbit. So now orbit needs to sort of do a couple more things to get the function running. So the first thing is needs to save the old EBP. So the EBP was the base pointer for main. It's pointing at the SFP of main. We're going to need this later when we return from main. So we need to make sure to store that. So orbit is going to store that. It's going to store as the SFP of orbit. And then it's going to move the EBP down. So now it's going to keep track of the base of the orbit frame. So we store the base of the main frame. Now we're going to change EBP to storing the orbit's base frame, which is the SFP of orbit. And then we can move ESP down as we add new variables in the orbit frame. So now this orbit can do whatever it wants to do. It can add new variables. It can do some logic. But once it finishes executing, then that's when calling convention sort of returns. What do we do to clean up this function now? So the first thing we're going to do, this is important for understanding ret-to-ret and also other memory safety vulnerabilities. But what's going to happen is we're going to move our ESP to our EBP. So we're sort of going to get rid of all the variables that orbit created. We don't need them anymore. Orbit has finished running. So we're going to move the ESP to the EBP. So that's where the start of the stack frame is, right? And the EBP's main job is to keep track of where the SFP and RIP of orbit is. Because Otherwise, we wouldn't know where we sort of kept those two variables for storage, right? We stored them on the stack. We need to be able to retrieve them. So we need to know where they are. So that's why we have the EBP. So the stack frame it's going to rise up to the EBP. This tells us, hey, right above this address is going to be our SFP. So then we can modify our EBP to be whatever we saved earlier. So we sort of restore the EBP to be the EBP of main. And then we have to restore the RIP. So this is what the return instruction does. It's going to pop the RIP off from the stack. It's going to move the ESP up, and it's going to set the current EIP to be back to whatever was stored in this RIP. So we're going to continue running code in main again. And then lastly, the main function is going to remove all of those arguments from the stack because it no longer needs it, because Orbit has already completed its execution. So yeah, this is what a normal function prolog looks like and a normal function epilogue. I think this is in the textbook as well. So this is just something important to understand for sort of understanding the flow of memory safety vulnerabilities, because a lot of them exploit this calling convention structure. Okay. All right. All right, we're going to move on to different attacks. So the first attack is the canonical buffer overflow attack. So how this works is we allocate some memory in our stack, and in this case, it's buff. And we have some function that allows us to populate that buffer. In this case, it's the guess function. And the issue arises when we're allowed to populate more than the size of the buffer that we allocated. So in this case, buff is 8 bytes large. But if we're allowed to overwrite more than 8 bytes, we can start overwriting things that are above buff in the stack frame. And if you recall from the calling convention slides, the things that are above, where our local variables are, is the SFP, the RIP. Those are things that we sort of saved on the stack that we expect to be the same when we come back. But when those changed, there can be some dangers, right? In this case, what we can do is we can modify the RIP to be the address of shellcode. And this is sort of the malicious code that we want to execute that causes something bad to happen. And if we overwrite the RIP with the address of shellcode, what happens is we would be able, once that function sort of finishes, right? Once the orbit function returns, calling convention is going to restore the EIP to be whatever was the RIP, whatever the RIP value was. And that means that we're going to restore the address of shellcode into our EIP, and we're going to start executing the shellcode code instead of the original function main that we came from. So this sort of disrupts the flow from main to orbit back to main. We're disrupting that flow and then causing us to execute shellcode instead. So this is sort of attacking that calling convention, the fact that we stored the RIP on the stack and we're expecting it to be the same when we come back. Another attack is an integer conversion attack. So this is when we're allowed to write more than we should also because of an unsigned-signed difference between variables. And so we're able to put in a negative number and then pass certain checks that allow us to do things that the program wouldn't expect. An off by one attack is also sort of attacking this calling convention idea. So sometimes when we write code, we might forget maybe it's less than or equal to. Sometimes we forget just a little bit and we allow the attacker to write not like a full canonical buffer overflow where we can overwrite whatever we want, but only 1 byte of our SFP, so 1 byte over. And this is still bad because what this allows us to do is it allows us to change the SFP to be something close by to where the original SFP was. And so I'll walk through that right now. So we can see here how this is the SFP and RIP of our function, right, on the very left. And we have our base pointer and our stack pointer like normal, like we're executing the function. And as we return from the function, right, we remember there's sort of 3 steps that occur, right? We move the ESP to the EBP. we pop the EBP and we pop the EIP, right? So sort of relating that to the calling convention from earlier, we're removing all of our local variables. We're going to restore the previous function's base pointer, and then we're going to restore the instruction pointer to be running in main. Yeah, did you have a question?
I think instruction might be wrong there. You said it right. It says move ESP EBP. I think it should be move EBP because we're moving the ESP to the EBP.
Yes, we're moving the ESP to the EBP.
So I think the slice has it wrong.
I believe it's to the the first argument should be what we're setting. So we're setting ESP to be whatever the value of EBP was.
Oh.
Yeah. Max, you can check what the actual x86. But yeah, the idea here is to set the ESP to be whatever the EBP was. Yeah. Okay, so yeah, sort of need to remember those three steps because those come up over and over again. We're going to remove the local variables, set the ESP to be equal to the EBP. We're going to pop the EBP, which means we're going to set the base pointer back to the main's base. And then we're going to set the instruction pointer to start executing the main's code again. But in this case, if we modify SFP, so we modify 1 byte of SFP, yeah, so when we restore the EBP, before the EBP would now go upwards, right? Somewhere above in our stack frame, and it would point to the base of main. However, in this case, if we modify this SFP, we can cause the base pointer to point somewhere down into some buffer that we have executing in our previous stack frame. So normally, we never see the EBP below the ESP. So the base pointer has to always be above or equal to the stack pointer. But in this case, we violate that sort of constraint because we modified the safe frame pointer to something that's lower than it should be. And so there's no actual check, right, to make sure that this constraint is held true, but it's sort of held true because of how calling convention works, right? So in this case, now the EBP is pointing down into our buffer because we changed this SFP, right? And then the next step sort of still executes while we're executing this program, we don't notice anything wrong, right? We're just sort of following the steps of calling convention. So the next step is pop EIP. So now we set the instruction pointer to whatever our RIP was. So we start executing in main again. That's perfectly fine. However, the problem is when we return from main, now we again follow the same three steps, right? We set our ESP to be equal to our EBP. And now instead of setting the ESP to the base of main, now we're going to set our ESP all the way down to somewhere in buff, whatever we changed the value of SFP to originally, right? And now we believe that we're looking at the main's SFP and RIP, right? We believe that the stack pointer right above the stack pointer should be the SFP of main, right above that should be the RIP of main. But instead, we're not, right? We're actually somewhere in a buffer that the user could control. And so now this is sort of like a fake stack frame that the program believes is the SFP and RIP of main, but actually the user can control to be whatever they want. So they can choose whatever new SFP and whatever new RIP they want, which means they can put the address of shellcode into that fake RIP stack frame, and we would begin executing the shellcode. So that's how the off-by-one attack works. A format string vulnerability is when we have a print statement, and usually the first argument of the print statement is a little bit special, right? That first argument allows us to set how we want to print the rest of the arguments that we pass in. So the first one tells us how to format the print statement, how to format all of the rest of the arguments that we pass in along with that first argument. So a normal print statement would look something like the first argument being maybe %s to format the next argument as a string, right? %s and then buff, right? That would be what a safe print statement looks like. However, we have an issue where if we pass in a user controllable buff as the first argument of the printf function. So when this happens, now the user can control how, sorry. Oh, why did it die? Okay, there you go. So now the user can control how the print statement is going to be formatted. And this is bad because the print statement, the print function doesn't really know how many arguments was passed into it, right? Based on calling convention, we know that the arguments are just passed above the RIP of the print function, right? Whatever is above there, that's sort of the arguments that are passed into the function. And so because we can sort of dynamically pass in a different number of arguments to printf each time we call this function, we typically know how many arguments the printf function takes based on that first variable. So if that first variable has, let's say, 3% modifiers, we expect 3 more arguments to be passed into the printf function. Now this is bad because, okay, I guess there's no. This is bad because now the printf function will start looking at higher and higher into the stack, looking for those arguments that it believes should be there, but actually is not because it's just the user adding some % symbols into that first argument. And so things to know about this is %n and %hn. So these are special formatters that allow us to write to specific addresses of memory. And so we would be able to overwrite parts of memory with maybe the address of shellcode, for instance. Okay, and yeah, the last attack that we have is the red-to-red attack. So this is also sort of attacking calling convention, how that works. And the main purpose of red-to-red is to get around ASLR. So that's something that we're going to talk about in just a minute. But ASLR means that we randomize the beginning sections, or where the stack section, heap section, code section, static sections, where those sections begin. So we randomize where that is in terms of main memory.
When you randomize, do you mean by like are the blocks of like say like the stack is still together, but like say like maybe the heap was below the stack, but now in this ASLR enabled version, heap is above stack. Like is that what you're meaning? But or what you're meaning is that it's totally broken. Each section of memory is broken up into chunks. Like it's like randomly spread out.
Yeah, that's a good question. So each section is still contiguous. So we don't split up the stack into 5 different sections and then put those in different places. We sort of keep the stack together, the entire stack, the entire heap, the entire code section. Those sections are still blocks that are together. We're simply randomizing where those sections begin. So yes, now the heap might be above the stack, maybe the code section's at the very top, right? But those are the starting location of where those are is randomized. Okay, so back to red. So if we do randomize those sections, a problem that causes for attackers is we won't know where the address of shellcode is. And that sort of is an issue because if we want to overwrite the RIP or overwrite something, overwrite the EIP to be the address of shellcode, we need to sort of know what the address of shellcode is. And so the way that we get around that in red-to-red is we're not going to directly overwrite the RIP with some address of shellcode, but instead we're going to try and find a pointer somewhere else on the stack that points to somewhere useful or relative that we can use then to exploit. So in this case, okay, so
Why can't we just like put the shell code in somewhere and then just like, or like, we could just like do a buffer overflow tap here and like put the shell code right above the rib and then change, oh, but
yes, you don't know where the shellcode is. You don't know where your stack is. So therefore, you don't know if you write the shellcode right above the IP, you don't know where that is. If you put it in some code section or some other section, you also still don't know where that address of shellcode is. You can, but it's randomized on each run. So you can check it once in GDB, but then the next time you run it to try and exploit, it will be different. Yeah. Okay, so okay. So in this case, this is sort of, let's actually start here. So we're going to overwrite addresses. So in this case, we found a pointer that's pointing to somewhere relative to our stack. And so we want to use this pointer to be able to sort of point back into our own stack frame. And so we're going to overwrite the RIP with the address of a return. So we're sort of assuming a couple assumptions here, but one assumption that we're going to make is that we know the address of a return. And if we do know this, we can overwrite the RIP with the address of a return. And if you remember sort of from earlier calling convention, return is the last step of the 3 steps of a function at block, right? And return specifically will pop the next value and set the EIP equal to that value. And so if we overwrite the RIP with a return, then we can simply we can sort of return back to whatever address that pointer is looking at. And so we can start executing or set our EIP to somewhere in our actual stack frame. And then from there, we can add some no-ops and add our shellcode directly into our buffer. And because we sort of returned back into our own stack frame, we can start executing instructions inside of our own stack frame. So yeah. Any questions about that? Or any of the other memory safety vulnerabilities? Okay. Right. Okay. So how do we defend against these particular attacks? So we notice that many of these attacks are sort of trying to overwrite the RIP in our stack frame. And so what we do to defend against this is we want to put some sort of protective canary in front of our SFP and RIP to prevent them from being modified. So the stack canary is sort of like some random value that we place between our local variables and the SFP and RIP and everything above that. And this sort of acts as a warning sign. Right? So we set it to be some random 4 bytes and at the beginning of our function call. And then we go about the same sort of executing our function. And when that function wants to return, we're going to check that that value has not been modified. And if that value has been modified, then we know that somewhere in that function, we try to overwrite the memory that's above the stack canary. So somebody may have attempted to try and overwrite the RIP of the function that we're currently in. And if we notice that the stack canary has been modified, then we can immediately crash the program to prevent our program from actually executing anything malicious. So this is sort of like a early warning system that prevents us from modifying the SFP and the RIP. So we make sure that the stack canary is below the SFP, so it sort of protects both the SFP and the RIP. So this also helps prevent against off-by-one attacks as well. Okay, and then what we mentioned earlier, which is ASLR. So ASLR is randomizing the start of each segment of memory so that it makes it more difficult to know where the address of shellcode is. Okay. And lastly, we notice that attackers might try and put shellcode into our stack, right? Because that's sort of the easiest location to put shellcode in. You sort of are taking in inputs, storing those inputs on the stack. And so it may be likely that the attacker is exploiting that and putting shellcode that it wants to run onto the stack. But we don't expect to actually run code on the stack. So non-executable pages is saying we don't allow any execution from the stack or the heap or the static section. We only allow code execution from the code section. And so this makes it a lot harder for the attacker to actually write shellcode to somewhere in memory and then start executing that shellcode. Okay. And lastly, pointer authentication is when you have a 64-bit, when you're working on 64-bit system hardware, you have a lot more bits for every single pointer. So 48 bits is sort of enough to get you to any location in memory. You still just have bits that are left over that you don't really need for pointers. And what we can do is we can sort of have a hash or a MAC of that first 48 bits to verify that the pointer has not been changed. So any pointer that we store in memory, we can sort of have like a canary, like an early warning system of that pointer getting modified that we can check every time we want to use that pointer. So we use those 16 bits as sort of like a pointer authentication code so that we can check to make sure that those pointers are not modified before we use them again. Okay. So the main takeaways is, writing C code is definitely really hard because you sort of need to understand really well how calling convention works. You need to write your own sort of making sure that your code is safe and you're not overriding things that you shouldn't be. So the easiest way to protect against this is using a memory safe language. Okay, it's 4:40. So does anybody have any questions about what we went over so far? Sorry, the screen keeps flickering. Anyone in chat have anything? Okay. Yeah, we're monitoring the chat as well. So if you guys have any questions, just go ahead and drop that in there. All right. If there's no questions, then we'll go ahead and get started on question number 1, Hulk smash. So you guys can take a look at the worksheet.
Okay, yeah. The worksheet can be found on the EdStem. Unfortunately, we don't have physical copies of the worksheet, so do any of you guys need the physical copy? Okay, cool. All right, so the first problem is Hulk smash. Let's first read through the problem. So it reads, for your inputs, you may use shellcode. You can also use the output, and you can slice the output for the Python syntax. All x86 instructions are 4 bytes long. For each provided code snippet, you run gdb once and discover that first, the address of the RIP of the Hulk method is at that address, FFFFCD84, and the address of a ret instruction is 080722D8. And then at the very bottom of the instructions, it says that ASLR is enabled, including the code section, but all other memory safety defenses are disabled. Yeah, so we have a function here. The first thing that we see is that there's a function pointer. So if you guys don't know what a function pointer is, that's okay, because for this problem, you don't really need to know how it works. It's just that it's a pointer to a function. So you can sort of imagine it as a pointer to an address in memory. Then we have two character arrays, buff and string. And then we have an fread function, which reads into buff from f, which is an input of this Hulk function. And then we printf the buffer using a string formatter. And then we fread into buffer from standard input. And then there's a length check on the eyes character pointer input. And then there's a str copy function that copies from eyes into str. Are there any questions before we continue? Okay, cool. So the first part, the first question is to fill out a stack diagram for the question.
Wait,
Do you guys want some time to do it? Okay, I'll give you guys 4 minutes to do the stack diagram, and then we can come back together. Yeah.
it says that including the arguments of Hulk. But we're not calling Hulk anywhere, so when you mean you have to put arguments of Hulk on the stack, do we just put I's and F on the stack?
Yeah, you can sort of assume that like there's a function somewhere calling Hulk. Yeah. Okay, cool. Does anyone need more time?
Yeah.
Okay, cool. So the first thing that we can do here is put the arguments of the Hulk function onto the stack. So remember that the order that these arguments are put onto the stack is sort of reversed. So here the second argument would be above the first argument. So it would be first I's and then F. And then we can put the RIP and SFP onto the stack. So remember that the RIP comes first and then the SFP comes after the RIP. And then finally, the next step is to look at the local variables inside this function. So there's three local variables, and the order that they're put onto the stack is the same as the order that they appear in the function. So we have our function pointer first. So remember that because it is a pointer, it only takes up 4 bytes of space. And then we have two character arrays, buff and string. And buff is 32 bytes and string is 28 bytes. So you can just put 32 and 28 somewhere in there. Are there any questions about this?
Is it if you don't put the data types and you just put like eyes,
Yeah, that should be fine. Cool. But you should specify the size of each entry. Yeah, cool. Okay, cool. So let's move on. So the next question is, we were given a few addresses in the question statement. So if we go back, it says over here, you run GDB once and discover that the RIP of Hulk is at this address and the address of a ret instruction is at this address. So my question for you is, are these addresses useful or not? To Hmm. So these addresses are actually not useful at all. The reason why is because ASLR is enabled. Um, and so the address values will change on every run of the program. And so just because they were equal to this in one run doesn't mean they'll equal to that in the next run. And so effectively, they are absolutely useless. Cool. So if they are useless, then we kind of have like no information on how to proceed with this exploit. So if you're sitting here in like the exam and you don't really know what to do for one of these questions, like a memory safety questions, a hint I'll give you is try to think about one of the questions from project one. Most of the exam questions will be very similar to one of the questions in project one. And so sorry?
which question?
That's my question for you guys. Which flag on project one is this most similar to?
7.
7. Yes, exactly. 7 because ASLR is enabled, and that's the only question or the only flag in project one that's enabled. Yeah, so the ret to wet flag on the project is very similar to this. So are you guys all familiar, or do you guys have like some faint memory of how the ret to ret attack works? Well, if not, no worries. So remember in ret to ret, the sort of motivation behind it is that first ASLR is enabled, and so we're not able to get the exact address of a shellcode. So even though like maybe we could put it somewhere inside this function, and maybe we'll know like exactly relative to something where the shellcode is, we're not able to override the RIP with that exact address. Which means like a simple stack overflow attack here won't really work. So the idea behind AS or ret to ret is that even though we don't know the exact addresses, we can use the fact that we know that the address to of shellcode is like somewhere near something. It's relatively close. So maybe it's like exactly 12 bytes above the RIP or something like that. And so we're able to use that fact to make sure that the shellcode is run on every run of the program. And so that's kind of the motivation behind ret to ret. The way it works is that there's like a bit of setup that you need to do. And we're going to see that in this problem. So the first step that needs to happen is that we need to put the shellcode somewhere in the program where there exists a pointer that points to it already. So here the only place that we can really put the shellcode is into this eyes argument. Because it is a pointer and like a it's like a string basically. And so the shellcode could actually fit inside there. Any questions about that? So the first goal is to put the shellcode into this eyes argument. And then the second goal the second goal is that we want this shellcode to run. And so to be able to do that, we need to be able to sort of interpret that address as an RIP. And inside ret to do that, we just chain a bunch of ret instructions starting from the original RIP up to this pointer that we have. And so if we look at the stack diagram here, we can see that the RIP is right here, and then the eyes argument is right here. So it's like two above the RIP in the stack, which means that we'll need two ret instructions, one at the RIP and then one at the file. And once that program runs, it'll eventually run the shellcode at the eyes part of the memory. Are there any questions about that? Cool. So yeah, so ret is an instruction that pops the value from the stack and puts it into the EIP. Remember that the EIP is the instruction pointer, so it points to the next instruction to be run. And so if we have a ret instruction that pops the eyes pointer into the EIP, then we're able to run the shellcode. And in order to do that, we sort of need to have this chain of rets that go up to the eyes pointer. So the next question is, where do you see a ret instruction that we can use? And so usually you would have to like look back at the problem statement, but you can see that in a sort of second box there is a ret instruction, and this box is described as the actual code of the green function. And so that's really useful because we have a function pointer that points to the green function. And so we can sort of infer that this pointer points very close to this ret instruction. In fact, it would point to the first no up here. Cool. And so the question now is, how can we get access to the value of this green function pointer? And we can sort of see, we can look back at the code and we see that there is a printf function on line 6. And this printf function prints the buff character array, which is a string. And right above the buff array is the green pointer. And so if we're able to make this printf print out all of buff and then sort of overflow into right above buff, which is the green pointer, then we're able to expose the value of the pointer right here and sort of be able to reference that in order to address the ret instruction. Cool. Yeah, so we can use the printf on line 6. And what that means is that all of the buff array needs to be non-null bytes. If there is a null byte inside the buff array, the printf will stop printing at that null byte, and we won't be able to see the green function pointer address. Yeah, and so we can use the fread on line 5 to fill up the buff to be just 32 bytes of garbage, where the garbage is non-null. And remember that fread, you'll have like a sort of appendix here, which sort of describes what like the arguments of fread are. But here the first argument of f read is sort of like the destination where we're reading stuff into. So we're reading into the buff array. The second one and the third number, you can sort of combine these numbers by multiplying them. So 1 times 32 is 32, and that's the number of bytes that are going to be read. And then that fourth argument is sort of the source that we're reading from. And so here f is the file, which is the argument from this function. And you can sort of assume that we have access to this file f. And so if we fill this file f with 32 garbage bytes, then the buff array will have 32 bytes of garbage after the line 5 f read. And then when we're printing in line 6, it'll print all of those 32 bytes of garbage. And then because there's no null byte, it'll continue printing above into the green function pointer. And then it will continue until there's a null byte. So if we're trying to, let's like assume that we're the exploiters and we're in some sort of like egg function or egg file. That's like a Python file, much like project 1. And this program prints out whatever print6 prints out. And we can sort of assume that's like set to the variable output. Then what indices of output do we need to use in order to get the green function pointer here? Does anyone know? So if the first 32 bytes that are printed are from the buff array, and we fill them up with 32 bytes of A's, and then right after that is the function pointer's value. That means that we want to slice for the 32nd index up to the 36th index. So something like that at the bottom. Cool. And so this is the address of the first instruction inside the green function, which will be the first line in that second box down there we see, the no-op, the first line no-op. So let's do a quick recap of what we've done here. First, we've stored shellcode into the eyes variable right there, the argument. And so now we know that shellcode is very close to the RIP of our Hulk function. Remember from the stack diagram, it was exactly 8 bytes above the RIP. The second thing that we decided to do is that we want to do a ret-to-ret attack, which means that we need to find a ret instruction and then put 2 ret instructions, one at the RIP and then one at the 4 bytes above the RIP, which is the F argument here. And in order to do that, we need to know the address of a ret instruction. And so we used the green function in order to find a ret instruction, and then use that one to do our ret-to-ret attack. And in order to get that the address of the ret instruction, we sort of use that printf on line 6 that exposes the value of our function pointer. And then now we can sort of do a bit of arithmetic to get the ret instruction address. Cool. So here's the stack diagram with the things filled out. So the shellcode is at eyes, and then buff is just 32 bytes. So that you can sort of imagine this is what the stack looks like after line 5. Okay, so now let's perform the exploit. Let's put everything together. So after line 5 runs, or after line 6 runs, the function is running an fread. Now remember that the first argument of fread is the destination where things are going to be put into. The second and third arguments, you sort of multiply these together to get the number of bytes that are going to get read. So 4 times 32 is 128. And then the fourth argument is the source that we're reading from. So standard input, this is something that us as the attackers can type into. You can sort of imagine it's like a terminal. You just type into the terminal and you press enter and then it gets read in. Yeah, so 4 times 32, 128 bytes from standard input, goes straight into buff. So let's look at inside the stack diagram, what bytes we have control over through this F read. So the F read starts at buff and it reads or it writes 120 up to 128 bytes. And so what we want to do, what the end goal that we want to do is we want to put a ret instruction over here at the RIP of Hulk, and then a ret instruction right above that too. And remember that these are addresses of ret instructions, not like the actual ret instruction itself. Cool. Which means that everything below that can just be garbage. So buff itself is garbage bytes. The green pointer is garbage bytes. The SFP is garbage bytes. And now the RIP of Hulk, we want that to be the ret instruction address. So we sort of did that right here. There's the output slice for the 32nd and 36th bytes. Cool. Here, the answer doesn't actually do any arithmetic to find the exact ret instruction because the green function just has a bunch of no ops that goes into a ret instruction. And so you could do a bit of arithmetic here, but not doing arithmetic will also work. And then we want to do the exact same thing on the 4 bytes right above the RIP of Hulk. And then that's all we need to do. Cool. And this is the final answer for the second part. Cool. Are there any questions on this problem? I know it's a really long problem. I would say that this is like above average difficulty for an exam question. Like this might be like the hardest question, the hardest memory safety question
Oh, no.
that you see on exam. Yeah, so yeah. Okay. If there's no questions, um, let's move on to the second question on the worksheet. I have no clue. Do you remember it being on the midterm? Okay, cool. So here we have a code snippet. So we have 2 functions. We have a main function at the bottom, which defines a 256 byte long character array, and then calls goldfish, another function. Goldfish takes in a character array as input. It calls fgets, which reads from standard input. It reads 256 bytes and then puts it into potato. And then we get the length of this potato character array and then store that into the chip variable. And then we print out the chip index of the potato character array. And we format that as a string. And then finally we run get_s into potato once again. So the assumptions are that stack canaries are enabled and all other memory safety defenses are disabled. And then none of the bytes on any stack canaries contain a null byte. And you run GDB once and find that the cola buffer is located at that address. Cool. So as usual, the first thing that we should do, even if they don't ask us, is to sort of draw out a stack diagram. So here's a stack diagram. I'll give you guys 3 minutes to draw out the stack diagram. Sorry, could you ask that again?
That's it.
Oh, yeah. Yeah. You can assume there's no padding on any of the exam questions, unless they say so. Okay, cool. Who needs more time? Okay, so let's start off. So they give us RIP and SFP of main, so that's kind of our starting point. So after the RIP and SFP, it's always the local variables of that function. And so there is one local variable in main, and that's just cola. Oh, sorry. Canaries are enabled. So there's a canary under the SFP. And then we have local variables. So it's just cola. And then after that, inside main, we're calling the goldfish function. So when we're calling a function, the first thing that goes onto the stack is the argument of that function. And so goldfish contains one argument, and that argument is called potato. And so they put potato, they called it potato instead of cola here. And then below the local variable or below the arguments is the RIP and SFP of the function. And then below the SFP is the canary. And then it's any local variables, and there's only one inside goldfish, which is just chain. Cool. So the answer choice of 1 and 2 was I think D and B.
There's a breakpoint at line 4. So technically, chip is not defined yet.
So good question. In C, the compiler allocates like space on the stack for local variables even before like those local variables are defined. So what really happens is that this sort of function is sort of like rewritten by the compiler such that chip is declared above line 2, and then the value is set like where it originally is. And so stopping this function at line 4 means that chip has like no value, like it's probably just random bytes, but it exists inside the stack still. Does that make sense? Let's move on to the next question. So this one asks us which vulnerability is present in the code. So that, does anyone have any ideas? Sorry.
Yes.
So gets reads from a standard input, and it just reads until a new line character.
Maybe there's a buffer. Yes.
Yeah, so that does technically exist. Um, but if you look at the stack diagram, remember that potato is a pointer to a character array. The character array that it's actually pointing to is cola, because that's what's being passed into goldfish inside the main function. And so, yes, we do have the ability to write past the end of potato or past the end of cola, but right after cola is the canary. And so, because of that, we don't really have the ability to overflow cola right now, unless we had the value of the canary, but we don't have that right now. But also, that's not really an answer choice here, unfortunately. So, if you see a question that's like this and you don't really know, you can just do like a sort of process of elimination. So the first one is off by one vulnerability. Off by ones usually happen when there's like a for loop, or like a while loop, or some sort of condition where you're like keeping track of a counter and making sure it's less than some number. So for example, like if there was a for loop in here and it was like for I equals 0 into I is less than or equal to 256, that would be an off by one vulnerability. But we don't really see that here. And so this isn't really an off by one vulnerability. The second one is signed and unsigned. This one's kind of hard to see, but in order to see this, you would just look specifically at the types of like integers. So we have one integer here, which is chip, and it's defined as an int 8. So int 8 is a 8-byte signed integer. The unsigned version would be uint, so there's a u in front of that. So chip here is a signed 8 bits integer. So that's cool, but that's kind of hard to really know what's going on. So the str length here returns a size type, or a u size type. So that type is a unsigned integer. You can sort of imagine that like the length of a string can never be negative. And so it doesn't really make sense for this function to return a signed integer. So yeah, so this is a signed unsigned vulnerability because at line 4, that function returns a unsigned integer, but we're storing it into a signed integer.
In general, so do you recommend us like just putting on that cheat sheet the data types of each of the inputs for like normal function for like common functions like fgets or like gets and stuff on our cheat sheet?
You could. I want to say that like that stuff would go onto the appendix, but yeah, so
Oh, it is.
I don't think like str length is here, but like I would imagine they would put it on here if it was in a question. But you can sort of see like these have like type definitions and size t. Um, it doesn't say what size t is, but size t is a unsigned integer. So for example, like if you're doing an fread and inside fread, you're passing in an integer into the second parameter, like a signed integer, that could be a signed unsigned vulnerability. In here, this is a signed integer. Yeah. So yeah, I think you could put like the function headers, putting down like what a size t is, like that's a unsigned integer would be nice to know. Yeah. And then the last one is format string vulnerability. So that doesn't exist here. We do have a printf, but because it's only printing the %s, like that is pretty safe. In order for this to be a format string vulnerability, the first parameter of printf would have to be like the actual buffer itself. In this case, it is not. So no vulnerability there. Cool. Any questions? Cool. Yeah, so assigned, unsigned. Let's move on. I'm gonna give you guys a few minutes to think about how we would exploit the fact that there's a signed, unsigned vulnerability here. Um, okay, so before you guys start solving the problem, I'm gonna talk about like the sort of idea of how we would approach this. Um, so the main problem in this stack is that there's a canary sort of in the way, and we don't have the value of the canary. And so yes, we have a get s that can write past cola, but because we don't have the value of the canary, it's kind of useless. And so remember from like project one and the canary questions, one way to get past the canary is to expose the value of the canary. And then when we're writing past it, we just write the original value back in. So that's kind of the goal here. Um, so what we can see here is that the only way to sort of expose the value of the canary to us is through that printf function. So somehow we need that the chip index of potato to actually like be the canary itself. And so the first sort of instinct here would be to make it make chip be like 256 because the 256th index of cola would be the canary because it's like right past the end of cola. The problem is that first chip is a signed 8-bit integer. So the maximum value of a signed 8-bit integer is 128. And so it's not really possible for a chip to equal to 256. So that's the first problem. The second problem is chip is getting set to the length of potato. And the length of the size of potato is 256 bytes. So it'd be really hard to make that function return exactly 256. Um, so the idea is that we can sort of use the fact that chip is a signed integer. And inside C or inside Python, you're able to index by negative value. And when you index by like -1, it wraps to the end of a string or like of a list. But in C, it's not that smart. So if you index like -1 of an array, it'll literally just go down the stack by 1. It won't like loop all the way back. So the idea is that if we have a pointer to like that we have the potato character array and we index some sort of negative value, we can go down to the second canary that's inside the goldfish function and use that canary instead of the one that's above the cola buffer. Are there any questions about that? Cool. So if we did some arithmetic, we can see that the second canary is exactly 16 bytes below the start of cola, which is our buffer. And so if we reference or if we index to the negative 16th byte, we should be able to read the canary. And because chip is a signed integer, that's possible. So if we somehow set chip to be negative 16, then our printf function on line 5 will actually print out the value of the canary. And in order to make chip a negative number, by setting it to a positive number, we just have to overflow that function or that number. And so string length returns an 8-bit unsigned integer, and then we're converting it into a signed 8-bit integer. And so in order to do that, the arithmetic is kind of like so. This arithmetic is honestly kind of tricky, but basically we're taking the maximum value of an 8-bit unsigned integer, and then we're subtracting by 16, which is the value that we want. And so we get 240. So 240 as an unsigned 8-bit integer. If we convert it into a signed 8-bit integer, it's interpreted as negative 16. And so that's kind of tricky. But you could sort of imagine, like, if you remember from 61C's 2's complement, um, if the most significant bit of a signed integer is a 1, that means that indicates the value is negative. So like 1 and then 7 zeros, like 1 0 0 0 0 0 0 0. That is the minimum, or yeah, that is the minimum value of that signed integer. So that would equal to negative 127. And then 1 0 0 0 0 0 0 1 is 1 greater than that. Um, and so if we want a negative 16, there's going to be a lot of ones in that number, which means it's a really big number when interpreted as an unsigned integer. Um, and so that sort of intuition should sort of hint you towards the fact that like it should be really close to 256. Cool. Yeah, so our input, or we kind of want potato to be 240 bytes long. And so we want that buffer to be 240 bytes of garbage. And then the rest can be anything else. So that's the solution to the F gets box. So 240 bytes of garbage, then a null terminator, and everything after that doesn't really matter. And so now chip should point to the canary, and now we want to read the canary in. So that would be like the first 4 bytes of output. And then now we can do a sort of normal buffer overflow exploit, and we just have the value of the canary, and we just put that where the canary is supposed to be. Yeah, so there's multiple ways to do this, as always. You can put the shellcode before the RIP. You can put it after the RIP. The solution here puts it before the RIP. So it's the shellcode, the corresponding number of garbage bytes to get up to the canary, then the canary, and then 4 bytes for the SFP, and then the address that we want, which is the start of our buffer, which is given to us in the problem over here. The cola buffer is located at this address. And so that's where we go. Are there any questions about this exploit? Cool. So the next part is assume that non-executable pages are enabled in addition to stack canaries. The question is true or false, this exploit still works. Does anyone have an idea about this? Yeah. Exactly. Yeah. So the answer is false because the shellcode is in the stack, which would be non-executable. In order for something like this to work, the shellcode has to be inside the code segment. So the exploit has to be like pretty different. Cool. So the next part is assume that ASLR is enabled, but non-executable pages is no longer enabled. Would it be possible to exploit this program with overwhelming probability? So overwhelming probability means like a decent chance. So like you can sort of imagine 50% is pretty good. But basically it has to be better than like 1 over like I don't know. Yeah. Does anyone have any ideas? So this is possible. Um so the printf here, remember that we used the printf to expose the value of the canary, but right above the canary is the SFP. Remember that the SFP points inside the stack segment of code, which means that if we do a bit of arithmetic, we can sort of derive the location of anything in the stack from the SFP of the goldfish. Yeah, and the only condition is that the SFP can't contain a null byte, and the canary can also not contain a null byte. But I think that was already true. Or maybe not. Cool. Are there any questions about this? All right, and that's all we have for our review session. There is another question on the worksheet, so feel free to do that for practice. The solutions are also for the whole worksheet are also on the EdStem. And then the slides are also on the EdStem. Cool. All right, good luck on the final exam. You guys will do great.